Okay, so let's start with session 3 of rocket propulsion of ARAM lecture series. So, till now we studied about the concept of we just in the first session we looked about different chemical propulsion systems. In the second, am I audible properly? Okay, in the second session we looked about the rocket performance parameters. We looked about C star CF. In this session, let's derive let's understand why the C star, the characteristic velocity, is dependent on temperature and molecular weight. Let us derive how. Let us see how it comes. So the topic is flow through rocket nozzle or 1D nozzle analysis. Before starting, the first I'll talk about the assumption. The first assumption that we are making, because in the derivation when we come, we simplify the equations by making assumptions, and there are some 4 5 assumptions over here. I'll explain you. First assumption is flow is quasi steady. Quasi means slow process. Steady means it has no variation with time. In thermodynamics, if a flow is happening fast, then it won't follow the exact cycle that it should follow. For example, the Brayton cycle, if the flow is supposed to follow a Brayton cycle, you cannot actually solve or plot for the Brayton cycle if it is not a continuous function. The flow should be reversible adiabatics. So reversible definition itself says the flow should be quasi or slow. Okay. Is my audible? Is my audio stable now? Can someone please confirm? Okay. So the flow should be quasi steady, that is slow, independent of time. Because if you see the steady flow energy equation SFEE, then the flow, if you have a variation in flow with respect to time, then you have another set of equation that you need to solve. But to simplify the equations, we have assumed it to be steady, that is no variation with time. Second point, flow is one dimensional. One dimensional, it as in there is no second dimension or third dimension considered for solving the equations. It is considered flow is just coming like this, no, like this, like this, like this. Third thing is fluid is ideal gas. Definition of ideal gas itself says it should follow the ideal gas equation. That is PV equals to nRT or P equals to rho RT, where P is the pressure, rho is the density, R is the gas constant, that is universal gas constant divided by molecular weight, T is the temperature. With constant thermodynamic properties, very important. If your thermodynamic properties are varying, then your performance will, everything will be varying. Actually, that is what happens. When I was making the solver, the prediction tool, we were using the variation change and the variated thermodynamic properties, but in this, for the simple, for now we just assume it to be constant and solve. What are thermodynamic properties? The C star, Cp, Cv and gamma, that is specific heat at constant pressure, specific heat at constant volume, and gamma, that is the ratio of specific heat, that is Cp by Cv. Everything is constant. Again, you can see here flow is one dimensional. In the rocket nozzle, actually flows goes something like this. So it has one this direction, one this direction. So it is actually a two-dimensional flow. And for rectangular nozzles, it is a three-dimensional flow. But for our calculation, let's see it is one D flow. And CP gamma actually varies with respect to space. With respect to time, we are considering constant, but in equilibrium, it is constant with respect to time, but with respect to local space, it varies. But for our calculation, we are assuming to be constant. Later, by derivation, we will see why it is constant. Next, fourth point is flow is isentropic. Isentropic definition itself says it is adiabatic and reversible. What do you mean by adiabatic and reversible? Reversible, I already explained you that flow has to go very slowly, slow step, and it has to be, and so that every step can trace back the preceding step. Adiabatic means there is no heat transfer across the walls. It means that whatever energy is inside is not getting lost outside, but in actual this is not the case. In actual, we know that from the walls, there is this energy transfer. The heat is, walls are conducting, so heat is getting transferred through the walls. But for calculation, let's assume there is no losses. Let's assume no losses in the energy, no heat transfer through the walls. Another point is no viscosity. Very important. Otherwise, there will be boundary layer, there will be boundary layer losses. We don't consider that. We consider flow to be invincible. Now, all the five assumptions are done. So, next comment. I will give you all the PDF. Don't worry, I will send you via mail. And if someone don't, I will also send you some other links. So, don't worry about that. There are four unknowns that we don't know at every step: density, velocity, pressure, temperature. And then we have four equations: conservation of mass, conservation of momentum, conservation of energy, and the fourth equation is the ideal gas equation. Now, why I'm telling you the condition of choking every time? Because it is very important. Because the downstream condition does not affect the upstream condition. So, critical condition for choking. Let's see why are we solving all these things. Why choking? When your flow is not choked, all the rocket equation will fail. No equation can be solved without choking. So, when your rocket engine is not choked, all the rocket equations fail. So that is why choking is a compulsory thing you need in your rocket engine. Let's see. Let's see. How do we derive? What is the and for choking there is a pressure difference required. So I will tell you how to calculate that. As I told you, it is a property of combustion chamber. Whatever is outside should not affect whatever is inside. But whatever is at throat will affect whatever is inside. So let's do energy balance. So how this is coming is basically we take SFEE, steady flow energy equation, steady, no time variation, flow energy equation. Steady flow energy equations look something like initial enthalpy plus initial velocity square by 2 plus heat addition minus work equals to final enthalpy plus final velocity square by 2. Now, there is no work done. First assumption. Second assumption, we took the assumption that the condition is adiabatic. Adiabatic conditions mean no heat transfer. This is 0, this is 0. The equation simplifies that as actually this whole term together called as H naught. So it means H naught 1 equals to H naught 2. H naught equals to H plus V square by 2. I mean, the H naught is basically stagnation enthalpy. Basically, if you stop the flow to complete rest after taking all the velocity, it is like reverse of ISV, a C star you can say. If you take all the velocity from the flow, make it stop, how much energy does it have? That's all. That is total stored energy or total potential you can say. Now, we will take 2 points. One is combustion chamber, one is throat. Because this is not a part dependent quantity. You go through any part, it will be same. It's like you go through one process, you go through another process. Just starting and ending point matters over here. That is why we take combustion chamber and throat, nothing in between. So Hc plus Vc square by 2 equals to Ht plus Vt square by 2. C stands for combustion chamber, stands for throat. In the combustion chamber, I already told you velocity is 0, no velocity. So 0. At the throat, we know that Mach number at the throat is 1. In the previous session only I told you condition for choking. Mach number at the throat equals to 1. This is the condition for choking. Here, from here. The flow is choked. H, H is the enthalpy, can be also written as Cp into T. If you have energy, you can write it as Cv into T. But enthalpy written as Cp into T. That is why rocket combustion is a constant pressure process. Because you see the pressure in the combustion chamber is constant. It means the rocket combustion is a constant pressure process and not constant volume. The bombs, the atom bombs, the atomic bombs, all the detonators are constant volume process. So you use this equation CV wala. But in the rocket propulsion you use H equals to CPT because it's a constant pressure process. In an atomic bomb, the pressure increases, the volume remains same. Here, the pressure remains same because the gases are exiting. You can write it as Cp into T. Cp is the specific heat at constant pressure. T is the temperature. So Cp into Tc equals to Cp subscript T. Cp T into Tt plus Bt square by 2. Now we took another assumption above that the thermodynamic properties remains constant. Means Cp and Ct will be same. Cpc and Cpt at throat and chamber. So I wrote it as Cp Tc equals to Cp Tt plus Bt square by 2. Divide the whole this. Now rocket equations are just about manipulations. Divide these equations by Cp into Tt, and Vt can be written as A, that is the speed of sound. Because I already told you at the throat velocity is equals to speed of sound. And speed of sound can be written as under root of gamma RT. In the previous session I gave you, or you can just Google it. So substitute this into this, you will get Cp into Tc equals to Cp into Tc equals to Cp into Tt into plus A square by 2. A can be written as under root of gamma RT, so A square will be gamma RT. You divide the equation by Cp as I already told you. So Cp will come in the denominator over here, and then you have this gamma RT. Tc equals to Tt plus gamma RT by 2 Cp. Derivation is not a problem. Understand the process. Derivation you can go and look on your own and you can decide. And R is the specific heat constant. It is universal gas constant divided by molecular weight. Then you divide the whole equation by Tt. I will tell you why. Here you get a ratio. It is dimensionless. This is a dimensionless number. This has to be dimensionless. To make it dimensionless quantity as of now you use Mayer's relation, that is Cp minus Cv equals to R. This is all about 12th grade thermodynamics. Doesn't matter you know or not. You can always go back to NCERT and revise it. With the help of Mayer relation, you can write as Cp equals to gamma R upon gamma minus 1. Substitute over here. So you get Tc by Tt equals to Tc by Tt equals to 1 plus gamma minus 1 by 2 equals to 1 plus gamma by 2 equals to Tc by Tt. Now you remembered we told that flow is isentropic, and the isentropic flows T2 by T1 equals to P2 by P1 raised to gamma minus 1 by gamma. Homework. You can always derive this comes by PV raised to gamma equals to constant, TV raised to gamma minus 1 equals to constant. Divide this, manipulate and get this equation. Very simple. Basic thermodynamics. So you get Tc by Tt as 1 plus gamma by 2, and Tc by Tt you substitute as Pc by Pt raised to gamma minus 1 by gamma. So you get this equation finally. Pc by Pt raised to 1 plus gamma by 2 raised to gamma upon gamma minus 1. Now, for rocket engines, the value of gamma is basically 1.13 to 1.3. Let's take the value 1.2, which is average. For value, I want you to do this calculation. Take around 1 minute of time, exact 1 minute. Yeah, take 1 minute and solve it. For gamma equals to for gamma equals to 1.2, what is this Pc by Pt coming out to be? If anyone comes up with the answer, please write or tell. Actually, yeah, Correct, 1.77. So for PC by PT more than 1.77, the flow will be choked, and for less than 1.77, flow will not be choked. Why? Because we have considered the condition of choking here. You remember, we here in the above we put VT equals to A. That is why we have this equation. And if you take VT less than A, then your PC by PT will be less than this value. That is why we derive this for getting the pressure ratio at which minimum pressure ratio at which your engine will be choked. For example, if your throat pressure is 1 bar, your chamber pressure should be at least 1.7 bar so that your rocket equations are valid. Otherwise, your equations won't be valid. So this gives you the minimum operating pressure of your engine. Yes, correct. So just understand why are we doing this. That is very important. That's what I told you most important for rocket engine because the calculations are based on the condition of choking. Now, this is done. Anyone has any doubt in this particular part? That derivations you can do on your own, no worries.
but those assumptions तो कोई प्रॉब्लम नहीं होता है क्या उससे
Sorry.
the assumption that we're taking but if we practically use them doesn't it lead to some problems.
It does not lead to problem. It's just an assumption. If you don't take assumption, for example, if you don't take any assumption and you can solve in maybe 2 years, you take assumption. I mean, you get 100% efficiency. You take assumption, you get 85% efficiency, but you can solve in 2 days. So definitely, an engineer would love to solve it in 2 days, not 1 year. But a researcher would love to solve it in 1 year and not 2 days. Depends what you want to do.
Okay, okay.
I've done both the things. So a researcher's mindset, just get it as perfect as possible. Engineer's mindset, just get it working. Looking on to the next, any other doubt? Anyone else? I think. Okay, you can always type off your doubts. I am reading the chats also. So let's move on to the next part. If you have any doubt, you can type anytime. I can answer that. Now we will be deriving the C star characteristic velocity. We will see how this characteristic velocity comes and why are we writing it as a function of time? Because now we are talking hypothetical. I mean, we are talking like in a thinking way that higher molecule. I mean, gave you analogy and explain, but let's do some mathematical. Let's prove it mathematically now. So for deriving C star, we start with the mass flow rate. So mass flow rate m dot equals to rho a v. Rho is the density, a is the area, v is the velocity. This is kg per second. If you want to check the dimension, do the dimension analysis. You can do rho is kg per meter cube into area is meter square, velocity is meter per second. Meter cube, meter square, meter cancel, kg per second. Dimensionally correct. M dot is rho a v. So we take at the throat because throat in the rocket nozzle, a throat decides the flow rate, nothing else, because it has the minimum area. Very important. Throat decides, actually decides pressure to some extent. I mean, if you want to operate at a particular pressure, then the throat will decide a flow rate. Now flow is independent of downstream condition. That is why we are taking throat because after the throat, I told you take whatever, it won't affect the upstream condition. That is why I always take the condition of throat because that throat is the last condition that can affect C star, and we always have the everything for throat because the Mach number is 1. So things become simplified. Otherwise, at other condition, at other places you don't know the Mach number. At the throat, you always know the Mach number. That is why we try to solve like the assumption based calculation derivation. It it gives efficiency. That is why we always say the efficiency about the rocket engine, but it at least gives you a very good place to design a rocket engine. So starting m dot equals to rho at the throat, density at the throat, area of the throat, and velocity of the throat, which is speed of sound, which can also be written as under root of gamma RT, as in the previous session we wrote. As I told you, rocket equations are all about manipulations. Let's do some manipulations. This equation divided by the density of the combustion chamber gases and multiplied by density of the combustion chamber gases. Okay, what do you get? M dot equals to rho T by rho C ratio rho C AT, and this value under root of gamma RT, because it was V, right? UT matlab UT means the velocity of gases at the throat. Then you write it as the speed of sound, and speed of sound you write it as under root gamma T. Now, as I told that, as I made the assumption that it is an ideal gas. So for ideal gas, PC equals to rho C into RTC, PT equals to rho T into RTT. R is same for both of them because of thermodynamic properties are constant. So you get the ratio of rho T by rho C. Rho T by rho C equals to PT by PC into TC by TT. And as I told you that the flow is isentropic, so TC by TT can be written as PC by PT raised to gamma minus 1 by gamma. And for throat, yeah, the PC by PT. We derived it above. See, PC by PT is 1 plus gamma by 2 raised to gamma upon gamma minus 1. We already derived it above. So maybe I'll just draw a chain connection so that when you're looking at it, you get to know what it is. It's a very long chain. Actually, not here. I will write it here. See, I you can write rho c by rho t as rho t by rho c as this term, and the whole term as rho t by rho c equals to pt by pc into tc by tt, and pc and tc by tt you can write in terms of pc by pt, and then you have rho c by rho t by rho c in terms of pt by pc, and pt by pc ratio, the pressure ratio, you have as 1 plus gamma by 2 raised to this value. So you get the rho T by rho C. It is gas dynamics, nothing else. Again, derivation is quite complicated, but you can always trace it. Then again, you have PC by PT by PC equals to TT by TC raised to gamma upon gamma minus 1. So you can derive these equations as well, because I will tell you why. Your m dot is rho T by rho C, and then this was rho C, which you wrote as PC by RTC. M dot equals to rho T by rho C into rho C into AT into VT. You wrote it as rho T by rho C into rho C P equals to rho RT. This will be PC by RTC. This will be AT. This will be under root of gamma R TT divided by TC multiply by TC. Just manipulation. This you have in terms of gamma, function of gamma. PC by R, PC let it be, AT let it be. You see here RTC, here RTC. So it will be rho T by rho C, PC, AT, root RTC into under root of gamma TT by TC. So this thing and this thing, you can write, see, TT by TC as a function of gamma. Okay. Rho T by rho C also we wrote as a function of, this is a function of TT by TC, so it will also be a function of gamma. Function of gamma. So the whole equation comes as m dot equals to PC AT by root RTC upon function of gamma. This term, and gamma is a dimensionless number. Basically, the RTC was very important. This term is called as C star. C. It is PCAT by root RTC upon this function of gamma. That is also called as capital gamma of gamma, some Kiskowski's function or something like that. And you can write this big term as C star. And if you observe the big term, C star is root. This this is basically a specific constant RU by M2. RU is constant. This is a constant value. The only variation is TC and molecular weight. Means that, and in the previous session we just wrote that C star is directly proportional to under root of Tc by molecular weight. Higher the temperature, lower the molecular weight, combustion is more, I mean, gases can be accelerated to more velocity. This is the derivation of C star. How C star came? It came from the mass flow rate equation. And why throat? Because the condition outside the throat does not affect the throat. So C star has no physical significance. It's a theoretical concept, but very important concept. It gives you the combustion efficiency of a rocket engine. Very important. Cool. Any doubt? Please start asking doubts.